twin primes and the twin prime conjecture. My motto: plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. This slide shows a Mod 6 sieve of Eratosthenes that has been abridged in order to show the first 6 twin primes. The Mod 6 sieve of Eratosthenes consists of 2 columns of numbers that contain all odd integers, with the exception of 3 and its composites. It therefore contains all possible candidates for twin primes, such as 5 and 7. 2. It also contains all twin primes for which there is only one possible configuration, the first 6 of which are given in the table. The first is 1113 with a composite of 15 in between, and 1719 separated by a composite of 3 which ends in 5, so 3 times 5 equals 15. 3. So the only possible configuration for a twin prime pair is that the last digit of the 4 primes always have the sequence 1, 3, 5 composite, 7 and 9, where the composite that ends in 5 always has 15 as a factor. 4. The table shows that all twin primes have modularity 6n-1 and 6n plus 1, so that twin primes must have consecutive modularity 6n-1, 6n plus 1 and 6n times n plus 1 minus 1 and 6 times n plus 1 plus 1. 5. Primes get scarce as the numbers get larger, and twin primes even scarcer, whilst twin primes get even scarcer still. So a demonstration that twin primes are infinite is also a proof for the twin prime conjecture that they also are infinite. 6. The only way to find the twin primes is to troll for them, and the next slide shows the first 30 and last 28 of the 898 twin primes in the first 10 million numbers. Programming is relatively simple and executes in 23 seconds using precise calculator by Petra Lastovica. The following 3 slides from the next 1 million candidates shows the first and last 27 twin primes from a total of 568. The first prime of the twin primes have all been subjected to a residual analysis using the progressive sieves of Eratosthenes by dividing it by the primorial that creates any one of the sieves. For example, 2 times 3 times 5 times 7 equals 210, gives a 48 column sieve. 2 times 3 times 5 times 7 times 11 is equal to 2310, gives a 480 column sieve. 2 times 3 times 5 times 7 times 11 times 13 is equal to 30,030, gives a 5760 column sieve. What we have done is to find the first value stroke header of the column that generates a prime such as 67,211, and by association its 3 companions 67213 and 672137 and 672139 sitting alongside it, 4 adjacent columns of infinite extent. 8. So we have established a group of 4 adjacent columns capable of generating infinitely many twin-twin primes. That is not to say that any of the residuals are prime and do not need to be so, only that the 4 values across the 4 columns can have any mix of composites and primes it is possible to have, and twin-twin primes are by far the least likely. 9. For the 210 sieve we have only 3 possible residuals, which are 11, 101 and 191, corresponding to the 2nd, 3rd and 4th twin-twin primes. So 3 times 4 equals 12 columns out of 48 is 25%. 10. For the 2310 sieve we find 3 times 7 equals 21 residuals, and 21 times 4 equals 84 columns out of 480 is 17.5%. This has been confirmed by inspection of the sieve, shown below. Only 6 of the 21 residuals are prime, shown red in the table. Counting the occurrences of the residuals in the first 897 twin-twin primes showed excellent equality across them all, and therefore no preference of any particular one as a twin-twin prime generator. For the 30,030 column sieve, I speculated, based on the previous 2, that there would be 21 times 11 equals 231 residuals, but I only found 196 via 2 lots of the twin-twin primes obtained by programming. See table on next slide 14. It was too laborious to pursue manually any further, so I managed to write a program to do it, and there are actually 252 residuals. Now 252 times 4 is equal to 1008 columns out of 5760, which is 17.5%. Taking this line of reasoning further, we see that as the sieves get bigger with each new prime, they soon start to get astronomically bigger, then infinitely bigger. The number of lots of quad columns amenable to the generation of twin-twin primes becomes infinite, an infinity of infinities out of infinity. The percentage, however, compared to the total number in any one sieve, will slowly decrease exponentially as follows. The 510,510 column sieve has 2,457 residuals times 4 is equal to 9,828 columns out of 92,160, which is 10.7%. The 9,699,690 column sieve has 36,855 residuals times 4 is equal to 147,420 columns out of 1,658,880, which is 8.89%. The next 2 times 3 times 5 times 7 times 11 times 13 times 17 times 23 column sieve exceeds the memory capacity of my computer. 12. To summarise: 1. Although very scarce, twin-twin primes are still an integral part of the prime composite formation process, and there is no reason for the process to stop simply due to increase in size of the primes. 2 4n plus 1 and 2 4n plus 3 primes are required to form twin-twin prime pairs, and both increase in size at the same rate, so coincidence is always possible, although highly improbable, as shown by the table on slide 17. 2. The high improbability is more than offset by the infinite increase in the sources of infinite extent from which they derive. 3. Because the composite that ends in 5 always has a factor of 15, yet 25 that follows does not, whilst 35 does, means that twin primes cannot come closer to each other than 30. There are only 4 twin primes that fulfill this requirement, and they are as shown. 4. To conclude, twin primes have a clearly defined structure and mathematical properties, and their existence is dictated solely by the constraints of the formation of the composites, for which they will always be required at some point in the process, no matter how infrequent, and therefore we can say that twin primes, and therefore twin primes, exist all the way to infinity, irrespective of their size. QED. So that's all, folks. Hope you enjoyed the maths, and thank you for watching. Bye.